Pradeep sir, am I audible?
Yes, ma'am. We are ready, ma'am.
Okay. You can proceed. Sir, Prabha sir, good morning, sir.
Good morning, ma'am. Am I audible?
Yes, sir. You're audible,
Okay,
sir.
ma'am. Okay, fine. Shall I share my screen, ma'am?
Yes, sir.
Ma'am, is it visible to everyone?
Yes, sir.
Okay, fine, ma'am.
You can see the full screen of your presentation, sir. Yes, sir.
Okay, ma'am. Okay, thank you.
Okay, so we'll start. Good morning, all. I have immense pleasure to introduce our guest speaker of this session, Dr. S. Prabhakar, Professor and Head, Department of Biomedical Engineering, and Director Research, of Dr. NGP Institute of Technology, Coimbatore. He has various additional portfolios as Director Research, Vice President, and MHRD, Institutional Innovation Council, a Deputy Chief Coordinator, Industry Institute Partnership Cell, and Convener, Center for International Relations. He received a bachelor degree in Instrumentation and Control Engineering from Madurai Kamraj University in 1999, and he has a good academic record with the Master of Engineering and a PhD degree in Faculty of Information and Communication Engineering from College of Engineering, Chennai, Anna University. And his specialization is medical electronics and medical image processing during 2014. He is a member of Board of Studies and Information and Communication in Anna University. Dr. Prabhakar is a senior member of IEEE, lifetime member of Indian Society for Technical Education, ISTE, and Biomedical Engineering Society of India. He is also a senior member of UACEE, the IRED, that is Institute of Research Engineers and Doctors, International Association for Engineers, Association of Engineers, and International Association of Computer Science and Information Technology, Singapore. He is also chairman of Sttp, Biomedical Engineering Society for Tamil Nadu section. He has 3 years of experience in medical electronics industries, 21 years of experience in teaching, research and development, and 13 years experience in academic administration. His research interests include medical instrumentation, graphical system design, medical image video processing, biosignal processing, biomodeling, cognitive development for disabled children, evolutionary computing, and bio-virtual instrumentation. He established various centers like Dr. NGP Center for Medical Equipment and Systems, Center for Medical Imaging, Medical Equipment Calibration Center, Center for Product Development, and PMKVY Skill Development Center on Medical Equipment Technology. He has published 79 technical papers in reputed national and international journals and conference and book chapters. He has also filed 5 patents of his distinguished research work. He served as chair, editor, and reviewer for many national and international conferences and journals with high repute, and also handled a number of industry government funded projects and schemes for the worth of 73.7 lakhs. With this brief introduction, I would like to hand over the session to Dr. Prabhakar. Welcome, sir.
Thank you, madam. Thanks for the nice introduction.
Thank you, sir.
First, I would like to express my sincere thanks to the management, principal of PSNA College of Engineering Technology, Dindigul. I am really happy to take part this faculty development training program. It's a good opportunity for me to share my experiences in this August gathering. For this opportunity, especially I would like to thank Professor Dr. Jayanti, Professor and Head, Department of Biomedical Engineering, and Professor Dr. Sudha, Professor in Biomedical Engineering. Thanks, really, my thanks for them for providing me this opportunity. The topic today, what I am going to discuss is harnessing intelligent biosensors and new frontiers in healthcare technology. I hope for the past few days, the participants have interacted with various eminent personalities and various experts with their, with different topics. Actually, the biosensors is the, really the needful topic at this juncture. Why I'm telling you this is every day we are exposed to new creatures, living creatures. We all know that this pandemic, the COVID-19 next mutation has come into the world, as well as which keeps on spreading like, compared with the earlier one, which is more rapidly spreading as well as more efficient than the earlier one. At this point of time, this particular topic, like biosensors, it's a very important and vital one, which has its own importance at this junction. Why I'm telling you this is, see, as a researcher and as a biomedical engineer, as well as the, let us say, healthcare professional, we are part of healthcare professionals. In that aspect, our responsibility is to invent or create a new device which should be very efficient to detect without touching or without, remotely we have to find the presence of that virus. For that, I hope this particular topic, biosensors, are very essential. With that only we are able to achieve that particular task or requirement. That is the need for us. That's why I said this biosensors topic. It's really very useful. And then another aspect, if you look into, other funding agencies, this particular biosensors topic are materials, are nanosensors, or nanotechnology, are the thrust areas for which the government are ready to invest huge funding. Okay, based on that, we are able to develop our develop our inventions, and we are able to create new devices and technology for the welfare of the society. That's the ultimate aim of. Oh, please excuse me 1 minute. Hello, Nitya. Sorry for the inconvenience. Am I audible now? Hello.
Yes, sir. You are audible, sir.
Audible? As
Yes,
well,
sir, yes.
are you able to see my screen?
Yes, sir. Yes, sir.
Okay. Sorry for the interruption. So in this aspect only, I said this topic is very important and essential.
Sir,
And then, yes.
sir, kindly give a full screen, sir.
Oh, 1 minute. I'll do one thing. Stop share. Sorry, there is a dual time which has been, 1 minute. Now, are you able to see my full screen?
Yes, sir. Yes, sir.
Okay, fine. Thank you.
Thank you.
So this, as I said, this topic, biosensors, with remote monitoring of this kind of COVID or any other disease, which is very important and plays a vital role. So we, the researchers, we need to develop the intelligent technology. Especially now, we are all know that highly flavored technology, artificial intelligence, and IoT, and even which are all support for the industry 4.2 revolution. In that context, we supposed to integrate this intelligent biosensor technology along with this AI technology, and then we go to derive highly efficient product to diagnose new diseases and new creatures. So that is the need for it. It is not only the purpose of diagnosing. Obviously, this particular biosensor as well as the other technologies will support for us to, have a smart home, to build the smart city. Uh, as a whole, as an outside, which is going to develop a smart city. If you look at this particular, front slide itself, you are able to understand that what I mean is, it is not only biosensor, that intelligent sensor technology or smart sensor technology, which is more essential to build a smart home, IoT enabled smart home, which provide us a comfortable environment for living. That is what we all expect. And then ultimate, how we are able to get a highly conducive and pleasant living environment. Obviously, for that case, we should be very healthy. The healthy are without any problem in our health. That is the ultimate purpose. That is the main core thing which give us, happiness. For that, we need to have different biosensors which supposed to be affixed with our body. Maybe if it is really required, we supposed to implant it. Otherwise, we can just wear it, and then through which we can continuously monitor our vital parameters, and then that could be transferred to the physician, and then the physician could be able to know and provide us the appropriate medicines or guidance how to lead our life to uphold it in a healthy manner. That's the purpose of this particular thing I have included here. The main agenda of my presentation is I wanted to discuss about smart sensors prior to discuss about the biosensors, because biosensors is the technology which is evolved from smart sensors. Then later stage, only the biosensor again that will be integrated with the smart sensor. Then the subsequent thing which we need to discuss about a few things about biosignal and image processing, which is the topic of this FDP program. So apart from that, I would like to discuss with you a few case studies, the certain projects for which we are all working. Some of the projects, my students or even myself, we put our effort and we work in that project that I would like to share with you in this presentation. So prior to talk about the entire thing, just I wanted to get clarified, like what is the difference between science and engineering, scientists as well as engineers. If you look at the scientists always strive to create new things or new innovations or new creations. That is what science. But engineers are engineering, which utilize that creation or innovations, okay, to solve the real-time problems in the society, and then at an outset they provide a conducive living environment for the society. So that is where the difference between scientists as well as engineers. So we, the researchers, should understand the roles of scientists, roles of engineers. Sometimes we, the engineers or scientists, we have to play this kind of roles. So sometimes we need to act as scientists, sometimes we need to act as engineers. As an outset, we have to have this both qualities to come out with good research outcomes. That's what my point here. Okay. Now, the smart sensor, basically the smart sensor are the technology which is developed especially for industrial applications. So in industries, various kinds of smart sensors are utilized. Maybe here we put some kind of processes going on, some temperature measurement, pressure. I mean, the objects are moving here and there. These kind of things are all taken place in an industry. So in that case, each and every sensor are very important, and then they are all, which plays, it has its own significance in industry, in process industry, especially, let me say. And then that parameter, what are the parameter that particular sensor which measures, which will be transmitted to a control room. From there, the engineers are, higher level scientists, they do monitor as well as they do analyze the parameters. Accordingly, they do control the entire industrial process. Okay. So now this smart sensor slowly, invade to various sectors now, which come into our healthcare industry, as well as, even as I said earlier, which is now integrate with the IoT, and which is going to provide us a smart home. Ultimately, as I said, which may lead to build a smart city. Okay, so that's the main thing. Now, the traditional sensor, if you look at this particular black diagram here, there is what are the components which are all involved with the smart sensor. So the smart sensor, basically the system under measurement, from there which measures the parameter, and then the transducers. These are all the things we all know very, very well. The transducers which senses the physical parameter, and then that will be converted to corresponding electrical signal that has been given to the signal conditioning circuit. From there, that will be transferred to the user or the person who is going to observe that parameter. Okay. Apart from that, which is not only to the system under measurement, which also have to monitor some the environmental kind of thing also. Why? Because what kind of environmental impact to be provided to my the process parameters, that also person have to understand. Okay, and then this is, you know very well, auxiliary power system, which is very essential. Without that, any of our circuit or transducer, any other system could not be able to function. Okay, so this is our regular conventional sensor system. Okay, but now if you talk about excuse me, sir, can you, any one of you can support me? There is a please, the window screen keeps on moving here and there. Any of you can support me? I think there is a, please move this window away from the shared application. Some information which is, pop up in my screen. Host, please, could you be support me?
Yes, sir. So share your PPT to HOD Bio at PSNACT mail, sir. We'll share it, sir.
Okay, okay. But it will take some time, is it right?
Okay, it's okay, sir. We'll pause the recording. And
okay, okay. Okay, I'll do one thing. Let me continue. In case of any difficulty again comes, then I'll.
Continue, sir.
Okay, fine. Let me continue now. Okay.
Yes, sir.
Okay. So now the smart sensors. Actually, smart sensors are the sensors and instrument packages. Mainly, see, as we actually earlier we have seen the block diagram, the functional units of the conventional sensor. Now, if you look into the smart sensor, here the smart sensor have the sensor technology, and then also having the conditioning, signal conditioning circuit. Apart from that, there is a processing unit. This is completely a microprocessor driven unit. Okay. Apart from that, which is also having its own communication unit, even some smart sensors also having the memory modules to store the data, because these smart sensors are put up in a, in industrial environment, or even that maybe, as I said, in a smart home environment, or which may be put up in the, wearable devices. And that case, that particular sensors could be able to take its own decision, and then accordingly, if it is necessary, it has to take some, it has to control the final control element of the system. That is also needed based upon the application where we are going to apply or use this particular smart sensor. So in this context, if you look at the small definition of this particular smart sensor and instrument packages uses the microprocessor driven and include features such as communication capability and onboard diagnostics. May I know any one of you could be able to, switch on your mic and tell what is that onboard diagnostic? Just I wanted to know that. Anyone of you can please? Okay, fine, no problem. I'll just onboard diagnostic. Obviously, you are come across this particular thing. This onboard diagnostic, which ensures the functionality of each and every modules in that smart sensor. Yes, they are all functioning in a normal way. It's a kind of self-test. Okay. See, without that, that self-test must be there. If there is no self-test, or there is no assurance of, yes, the particular sensor or particular signal conditioning circuit or whatever it may be the component, if it is if it is not ensuring that there is no proper functioning of that particular element, then the outcome you could not be able to get as per the requirement or as per our wish. Okay, so in that aspect only, that onboard diagnostic plays the vital role. As well as this onboard diagnostic will also support us for troubleshooting the problems persist or problems which has occurred at in the system. That is also very important. Okay. This onboard diagnostic that provide information to monitoring system and to operator to increase operational efficiency and reduce maintenance costs. So now you are able to understand with this particular smart sensor technology will provide highly optimum solution for the earlier one. Okay. Now, based on that particular earlier discussion, now if you look at the traditional block diagram of traditional sensor system as well as the present sensor, the smart sensor thing, which has its own A to D converter. Then, as I said, your signal processing or central processing unit, microprocessor unit. Okay. Then, which has its own local user interface and data storage as well as communication modules. This is what I said. These are all the other peripheral systems to be integrated with the the smart sensor. Okay. Basically, the smart sensors which has its own intelligence, because as I said, there is some kind of decision to be taken by the smart sensor itself based upon the physiological parameter or physical parameter which has been measured either at the industry or either in the body or at the home environment. Okay, so this particular smart sensors are capable of manipulation and computation of the sensor derived data or the physical parameters. So basically the sensors plus interfacing circuit, if you put it together or integrate both together, then we are able to derive a smart sensor. This smart sensor has the capability to do logic functions or two-way communication. The two-way communication means it has to measure, which has to take decisions based upon that, which has to give some kind of activation, or which should be activate the actuator, activating the actuator, okay, by providing some kind of or actuator or final control element, let me say, and then through which has to control the physical or physiological parameter. That is the ultimate purpose of this two-way communication. Okay, then which has to have, as I said, which has its own decision-making capacity. Okay, that is also very important in the smart sensors. Okay, that is IEEE 1451.2 specification has its own definition of smart sensor, which indicates that a sensor that provides functions beyond those necessary for generating a correct representation of a sensed or controlled quantity. This function typically simplifies the integration of the transducer into application in a networked environment. So this is again the subsequent block diagram, very simple diagram of the traditional sensor as well as the smart sensors. Basically, a sensor producing an electrical output when combined with interface electronic circuits is known as a smart sensor. So it is a combination of both sensor and actuator. This is what I said. Okay, both sensor and actuator, and then simply physical, biological, or chemical input that has been converted into corresponding electrical output as well as corresponding digital format. So what will happen is at the end, again, even though it's a digital, the compute, the microcomputer or mini computer which computes, and then the final outcome again that will be fed into as a physical quantity for controlling the physiological parameter. Now, the main usefulness of silicon technology in smart sensors. This particular thing, why we need to discuss about is this silicon technology are the highly essential and real revolution for developing such a good or precise smart sensors. Without this silicon technology, earlier and all, if you wanted to measure a temperature, or if you wanted to build a circuit, this is a very large in size. We supposed to have a big size of racks, or the people who are all exposed to industrial environment, especially cement industry or some kind of process industries. If you exposed to that, you might be seeing very big panels. Different sensors, all are big things. Okay, for that the handling and store the building fabrication thing itself, it's a very big in size. We require a huge space to accommodate everything. So these are all the difficulties what we face. But the silicon technology or integration of system on chip will provide us a highly precise, and then we are able to have a tiny component which has very high signal handling, or as I said, various physical parameters, processing. All those capacity is can be done in a simple, even a handy units. So that is the advantage of this. But now, if you look at this sensor, which has been integrated with microcontroller or microprocessor on board, and then a transmission system, all put in together, which will become a very, which may be equivalent to our palm size only. Okay, so easily we are able to handle, we are able to put it in the locations, and then that can be able to control precisely the processes. That's the advantage of this particular technology. So mainly the highlights single chip solution, very small in size, less space in configuration, work with small signals. So those are all the high advantage of this particular silicon technology integrated with sensor technology, so that we are able to derive good precise smart sensors. And then especially the smart sensors enhances various things, like self-calibration. That's what I said. See, especially all the smart sensors has the self-test feasibility. Based on that particular, feature, what will happen is, which ensures, yes, myself, I am functioning good. This will be ensured or assured by the smart sensor itself. And then, which has already, this is also we discussed, which has the capacity to do two-way communication. Okay, that is also done. And then similarly, computation, which has its logic, operations through which will be exactly compute the physical parameters, and then that takes the decision. Okay. And then another important thing is, this is the highly important nowadays, when the smart sensor technology got evolved. At that time, the technology has been developed for example, if you take one sensor, that particular sensor will measure or use for only one parameter. For example, if you use one temperature sensor, that measures only temperature. If you take another sensor, which is going to measure only pressure. But later stage, now the technology rapidly growing, through which we are able to develop a single smart sensor can measure various parameters like pressure, temperature, humidity, gas flow, infrared, chemical reaction. So many various parameters could be able to measure by a single smart sensor. That is the high capacity of multi-sensing smart sensors. Okay. Then why we go for this particular thing? If you take each and every parameter, different sensors, obviously the cost of the sensor goes high, as well as which also require again the space to accommodate all those things will be a little bit higher than a single sensor or multi-sensing smart sensor. So in that aspect, which reduces the cost of smart sensor also. Now, if you look at here, there are various components in the smart sensors that already we discussed actually, even though something different like network capable application processor and then transducer interface module. See, the network capable application processor, which is the unit which supports for different applications. Let us assume, for example, I think you people might have seen the National Geographic Channel and all. If they wanted to analyze what is the number of tigers available in that forest, otherwise what is whether the entire what do you call the humidity level or some other parameters in the environmental conditions are very precise or good or not. If they wanted to measure such kind of analysis, what they are doing nowadays is they make a tiny small sensors which is decomposed with the nature after certain time period. That is how they prepare or they make such sensors, and then just they throw in the forest environment. From there, each and every sensors are networked together, and then which will transfer the signal to the base station. So what will happen is, the persons who wanted to take such a survey or analysis, they need to invade into the forest. They can sit at their camp. From their camp itself, they are able to receive all the inputs from the sensors which are all, they just throw it around the forest area, through which they are able to get the signal, and then they are able to make all analysis. Again, what will happen is, over a period of time, how much power backup is there until which will be communicated. After that, which will be decomposed with the system environment itself, which won't be, give any impact to the thing. This kind of invention, this kind of analysis going on. This is what the network capable application processing, because which is going to build, multi-port networks through which is able to communicate. That kind of technology is available nowadays. Okay. Then if you look at this, the architecture consists of sensing element, transaction element, amplifier, sample and hold circuit, analog multiplexer, A to D converter, offset and temperature compensation, a DAC, memory, serial communication, processor. These are all the things we know very well. Okay, so with that, there is a small, simple block diagram of a sensor. See here, there is a generalized architecture. Here, if you look at, there is a sensor. With this sensor, you are going to make measuring various parameters. So based upon the parameter what you are going to measure, accordingly the sensor is going to change or vary. That's it. Okay. Remaining system, remaining circuit and all are almost similar. Maybe the amplifier, the gain value or structure, maybe we need to change, but all other components are almost similar for all the smart sensor architecture. Okay. Now, the architecture consists of, as I said, there is a central processing unit. So this central processing unit, sensor, battery, memory, and then each and everything, let us discuss here. The multi-sensor system, the sensor system uses information of several sensors to define knowledge of an environment. This is what I said. Here, if you look at the various physical property or physical parameters, temperature, force, acceleration, flow, position, each and every physical parameters has its own sensor unit. Again, what sort of output we are going to, getting it from the particular sensor, that plays the important role. Okay, based on this parameter only, output, electrical quantity only, we are able to build the circuit. Okay, the corresponding circuit as well as corresponding A to D converter, processor, and which environment this particular circuit or sensor system is going to function. Because I cannot choose, as I said, the smart sensor system which I put it on the forest, the same sensor system I could not use it in the in terms of boiler environment. Okay, or the same system could not be, same sensor could not be used in the some other highly freezing environment. So accordingly, according to the environment, we need to change the circuit system as well as the sensors. Yeah, this is the IEEE family standards with respect to smart sensors. Okay, as I said, 1451.0, which starts 1451, family standards. We see each and every standard has different phenomena that we should understand for developing or manufacturing such a sensor. Now, this based on the architecture, the central processing unit, if you look into the central processing unit, we all come across this central processing unit plays a vital role, which includes microcontroller unit as well as microprocessor based units. That's it. These two things, as engineers, we all study from our engineering engineering, UG to even PhD or whatever it is we are doing, any research we are doing. As an end, this particular technology keeps on evolving, as we discussed, based upon the silicon technology evolution, which keeps on growing. And then see the technology also come into manifolds. Now we have to decide which unit I am going to use it for my application. That we need to decide. And then one more thing, we keep on say that we need to choose suitable technology for suitable problem. For suitable technology for appropriate problem. Otherwise, both the things having any kind of mismatch, then you may not get the precise result out of it. That's a big challenge. Okay. So, and then this ASIC technology also, this is also another important thing that we need to consider. Okay, here there are, I have shown various different boards. Similarly, again, this also again extended thing. Iris, Muin, EZ, BeagleBone, okay, BeagleBoard. See, this BeagleBone at all, quite normally we people are using it for our even Raspberry Pi and Arduino. These are all things we are all regularly using it for our projects. Okay. Then battery module also again, which is also keeps on evolving, because in the early days, the battery has the capacity to deliver you maximum of, half an hour or 1 hour time. now you are able to extend the battery lifetime up to 8 hours or even 24 hours, like that, which keeps on developing. Again, for that, the entire internal structures and then what are all the, chemical compositions out in the battery, everything got changed, keeps on. This again, it's a, good research area. Many of the electrical and electronics engineers, they put their effort and then they are keep on developing the things, as well as this photovoltaic cells and all. Based on that, as I said, if you put or throw the sensors everywhere, what will happen is it will depend upon no need to be solar, any kind of renewable energy sources through which we have to energize the batteries. That kind of research work we need to adopt, and then we need to work on that part. And then commercial hardware structure, yes, it's very, very important, because as an outset or end, ultimately we need to provide the entire thing to the societal welfare or industrial welfare or industrial requirements. So in that case, we need to understand what sort of commercial architectures could be able to provide, as well as how much, again, at the end, with all our, coming to the end point, like how much cost effective it is. Then only the people will come forward to take it up and then use it, maybe for our smart home or maybe for wearable system or any other industrial applications. Okay. Yeah, this is again communication module. This communication module, this is what I said, which could be each and every different sensors could be able to make it as a network kind of thing, and then that will be transferring its signal to the base station. So this wireless sensor networks is, again, you all know that there is a different area, different domain, which which rapidly this is also growing. Okay, just I'll skip that point. And then the smart sensor network, this is what I said, from wireless sensor network to this smart sensor network, integrate together only, we are able to, derive the remote monitoring. Okay, now I'll almost, okay, that various types of smart sensors, almost we discuss about the architecture, structure, and then what is the basic fundamental blocks of smart sensors, all those stuffs we discussed. Now here I have given few types of smart sensors based on its principle. Just I will rush up these slides because these are all the things you know very well. We don't need to spend much time to discuss about all these things individually. Just I'll rush up these slides. Okay, optical sensor, infrared detector array, accelerometer, integrated multi-sensors. These are all the things. Now, you know the principle, based upon the optical or photon principle. When the photons fall on some substrate, this is going to generate its equivalent output voltage or current. Accordingly, this particular thing is going to work. So this is also, again, more useful for remote measurement. Similarly, infrared detector. Okay. I think these are all things we know very well. Now let me skip again. Yeah, infrared detector. Then next thing, if you see that accelerometer. Okay, so mainly that accelerometer itself is a metal coated silicon oxide cantilever beam. Okay, that is fabricated on the silicon chip, where the capacitance between the beam and the substrate provides the output signal. So this is also another important thing. So accelerometer are almost, they are all useful in almost all devices. Maximum device accelerometer nowadays we are using. Okay, or gyroscopes we are using. Okay, then integrated multi-sensors. This is what I want to tell you. As I said, this particular multi-sensor has various sensors which is working based upon various principles. Okay. So what will happen is, in this aspect, if you look at this, this chip contains metal oxide semiconductor devices for signal conditioning with on-chip sensor, a gas flow sensor, an infrared sensing array, a chemical reaction sensor, cantilever beam, accelerometer, surface acoustic vapor sensor, a tactile sensor array. So if you look at this, all these things all are working with different principles to measure different parameters. But all these sensors put in together are integrated together to derive or to develop a multi-sensor. Okay. This chip is fabricated using conventional silicon planar processing, silicon micro machining, then thin deposition techniques. So these are all the different silicon technology through which, based on which only these multi sensors are developed. Yeah, you just see this picture which gives the multi-sensor unit which is available in the University of California. Okay, main advantage, minimum interconnecting cables, similarly highly reliable. Then the performance is also very good. Of course, actually easy to design in terms of the subsequent thing, but the integration or the development of that particular technology, it is little bit complex. But later stage, the end user who are using those sensors, they need to have various circuitry, or they need to make more complex circuit. That's the purpose of this, easy to design and use and maintain. Similarly, scalable and flexible, small rugged packaging, minimum cost. That's the advantages. Okay, similarly, since it is measuring various parameters using the multi-sensors, of course, we are able to apply it for various different applications. That is also possible. Excuse me. Yeah, here this particular slide indicates the advantage and disadvantages of smart sensors. Okay, I don't need to discuss much about this. Let me go to the next slide. Yeah, here I wanted to convey you a simple thing about biomedical engineering. Most of us, we all come across this, but even though I wanted to remind that this particular biomedical engineering, which always deals with the wide spectrum of life sciences, because this biomedical engineering is a multidisciplinary domain which deals with not only human, which is also deals with animals, plants, insects, even I always say, which always deals with even a single cell living organism. So single cell living organism to the highly intelligent human being. It's our field which is going to deal with the wide spectrum. Okay, that's what biomedical engineering. The study which deals about only human being, that is called as medical science. Okay, and the study engineering principles in medical science, that is called medical engineering. But the study engineering concepts which is applied to all living creatures, that is called biomedical engineering. Yeah, this simple descriptive slide, let me skip this. What is the role of biomedical engineering? Okay, this particular technology, it's really a new promising interdisciplinary field. That's what I said. Biomedical engineering is a new promising interdisciplinary field. The ultimate aim or goal of this particular field is to provide improved healthcare for not only human, it is for all living creatures, including plants. That is the ultimate purpose of this particular field. Yeah, here, what are all the fields involved in the biomedical engineering? That just, given this, let me skip this. Then what is bioinstrumentation? This also we know very well. So I just do skip this because this biomedical instrumentation and the subsequent, various, signal analysis, data collection, these are all the kind of things, highly relevant to this FDP's title. Okay, so just that's why I have given a few slides about it. The main objective of the instrumentation system is gathering or collecting the informations from the body and doing the diagnosis and evaluation. The evaluation concentrates about what is the level of the disease or what is the severity stage of the disease. Okay, that is what the evaluation. Then based on that, what kind of treatment could be able to provide. So that is the part taken care by the physicians, but for that also they do depend upon the biomedical instruments. Then continuously the monitoring, the treatment process, whether it is in a highly positively progressive or it is deteriorating the patient's health. So all these stuffs to be analyzed by the system, and then which has to provide control on what extent this kind of treatment or this kind of thing to be delivered to the patient or delivered to the, system, that they need to understand. So this is the basic objectives of medical instrumentation system. Okay. So mainly this information gathering, measurement of phenomena to understand the system. That's what the phenomena thing, but in terms of the biosignals. Then diagnosis, detection of malfunction, pathology, and abnormality. Monitoring to obtain continuous periodic information about the disease. Then system, therapy, and control. Modify the behavior of the system and ensure the result. Evaluation, the objective analysis, proof of performance, quality control. And then at an outset, identify or analyze the effect of treatment. This is what the biomedical application domains we do concentrate, we do work. So this is a simple component of a man-machine system. You please look at this. I don't want to speak much about this because these are all the things we already discussed. But this is the fundamental blocks for biosignal acquisition as well as processing unit. Okay. So with this, you can understand. It starts from biosignal from a physiological system, and then a smart sensor or transducer technology, and the circuitry, then which is having a central processing unit, along with here the communication modules and storage systems are not given, but even though that are integrated along with this unit itself, and then this itself lead to analysis, and then again after the analysis the corresponding control is to be delivered, maybe a drive or maybe a physical exercise treatment kind of thing, or any other therapeutic applications could be directly delivered to a subject or a human. That is how the system completely closes. Now, after discussing all these things, will lead to a biosensor. So basically the biosensors, what is the difference between biosensors in terms of the earlier system or sensors, smart sensors, what we discussed is the biosensors has some kind of chemical reaction. Actually, we all know that generally this particular field, biomedical engineering, or the entire system itself evolved based upon the the biological systems has its own potential. That is the fundamental phenomena. From there only the entire technology gets evolved. So based on that, there is a kind of ionic exchange take place between some chemical solutions that produces some potential. Okay, so this particular fundamental phenomena only be the core of evolving or developing this particular biosensor technology. So based on that, if you look at a biosensor is a self-contained integrated device that is capable of providing specific quantitative or semi-quantitative analytical information using biological recognition element, which is indirect spatial contact with the transducer element. So what will happen is the biosensors are not directly equivalent to bioanalytical system, but which leads to bioanalytical system. Okay, an enzyme or electrode is a biosensor. This is the important thing, because analytical device which utilize biological reaction of biochemical molecule for detecting target analyte and converts their biological response into quantifiable and processable signal. See, mainly this particular thing, biosensors delivers or bind with the corresponding specific, reaction take place with the specific compound, then which develops the potential or which develops the biological signals. That's it. So a biosensor, any device that uses a specific biochemical reaction to detect biological compounds, biochemical compounds in biological samples. This means that, see, there is a compound which won't react with all the biochemicals. What will happen is which is going to have the particular positive reaction with that particular compound only. The remaining adult, which may lift, or some cases only there may be adverse or adverse effect may occur. That's why always we all talk about any allergy is happening or any allergy is occurred while they take any medicines or while they affix any biosensors along with the body. So these are all the things are highly fundamental. As I said again and again, major, very simple core in layman's words. Any two chemical reactions take place in the fluids, that is going to develop ionic exchange, that is going to develop some potential. This is the fundamental phenomena, which from there only the entire thing has been evolved. Okay. If you look at this particular diagram, the chemical to be tested, which has been superimposed along with in the petri dish, where the yeast cell is there. Here, the DNA repair gene, which is going to be mutated by the, jellyfish gene produces fluorescent protein whenever DNA repair gene is activated. Both joined together, which is going to generate a bright green glow, reveals the possible carcinogens. So it's a very simple diagram, just which indicates this kind of bindings and reactions, how it is going to, useful for identifying a particular, disease or whatever it is. Here it is carcinogens in terms of cancer cells. So see, which is going to be, we are able, the physicians can be able to easily analyze that input. So the basic characteristics of a biosensor, if you look into that, it should have the characteristics like linearity, sensitivity, selectivity, and response time. Of course, linearity of the sensor should be high for the detection of high substrate concentration. If it is not linear, of course, that is not providing a correct result. Okay. Then sensitivity, of course, once if you apply a sensor, once if you put a chemical, immediately the reaction should take place. Instead, the receptor, it took long time to absorb that chemical. Then obviously there is no, the response time will also, again, that will plays the vital role, because the response time is very high. Then nobody is willing to take up that work. Okay. Of course, let us assume, for example, for testing a COVID, already they said 2 days to get your result. Now they are all providing the results within 2-3 hours. Okay. So main thing is how much time we need to spend to get the result. Okay. And then, as I said, this is what selectivity, chemicals interface must be minimized for obtaining a correct result. If it is binds with, if the chemical what we apply, it gets reacted with various substances, and then which creates different outcomes, then obviously which confuses the result. Okay, so the chemical interface must be minimized, so to create a correct or exact or precise result. So here the correct definition of biosensors is a sensor that integrates a biological element with a physiochemical transducer to produce an electronic signal proportional to single analyte, which is the conveyed to a detector. Okay. Again, now if you look at here, the biosensor, physical component and biological component. The physical component consists of transducers and amplifiers. So biological component, sensitive bioelement and analyte. So these are all the combination of things are available in the biosensors. Here, this is the simple diagram of a biosensor. So the biosensor has the biological component, which is the analyte and bioreceptor. So this bioreceptors will receive the corresponding analyte only, which won't react with other substance available in the analyte. Okay. This bioreceptors has enzyme, antibody, microorganism, and then with this only the analyte is going to react. So based on this reaction, we all know, as I said, which is going to develop some kind of potential. So that potential only be our interest as a biomedical engineer or electronic engineer or instrumentation engineer. Our interest is we are much more concentrate on that particular potential which has been generated or which has been developed out of it. With that sensors, that potential is going to be acquired in terms of electroactive substance, pH change, heat, light, whatever the principle we adopted in sensor technology. We can use any technology through which we have to acquire those signals, and then that should be converted into corresponding electrical output, and then those electrical output will be given to a signal conditioning circuit. That is how we are going to develop the entire system or in terms of instrument. Okay. So this is what the basic structure of the biosensor model. So now you look at here response analysis. This is the earlier diagram only we put it here in a simple way. So in a sensor unit kind of thing. Okay. This response only be acquired and then observed. Okay. Observed by the these things only be sent to signal conditioning circuit, and then from there we are able to develop the entire instrumentation system. Yeah, basically this is what I said. This particular substrate only be integrated or interfaced with the corresponding enzyme only. If there is, it is incompatible, obviously that skip, and then these things will be left out. There won't be any kind of reaction should not take place. In case rarely any kind of adverse reaction took place, that kind of thing only be the critical. Yes, of course, while taking the research, the people will study all those stuffs, what sort of adverse effect, what kind of reaction took place, everything they do analyze, and then based on that only they will do work. Excuse me. So in this, the first component is biological element. So microorganism, tissue, cell, organelle, nucleic acid. These are all the very basic, the component used to bind the target molecule. Okay. Then second component, if you look at, that is acts as an interface. So here, see, after binding, this is what I said. After binding, there has been some kind of physiological, changes. Due to that ionic exchange, some physical changes take place. Out of it, some kind of, output or potential, biopotential is going to come out. So this is acts as an interface, measuring the physical change that occurs with the reaction at the bioreceptor, then transforming that energy into measurable electrical output. That's what I said. Okay, measurable electrical output. Then the third component is we are going to take that potential and then which has been delivered to a transducer circuit. From there, the transducers will be converting it into corresponding exact electrical quantity, and then the electrical quantity has been fed into signal conditioning circuit. From there, we are going to develop a complete system or instrument. So the type of biosensors, if you look at here, there are different biosensors or different applications: calorimetric thermal reduction biosensors, optical biosensors, resonant biosensors, piezoelectric sensors, ion sensitive sensors, conductimetric, amperometric, potentiometric. These are all the various types of biosensors right now available in the market. So I'll just skip this because each and every sensors we know very well. Optical sensor, resonant sensor, these are all things we have come across. So just I skip. Okay. And then what are the different categories? Clinical biosensors are used for clinical and non-clinical. Again, clinical also, again, in vivo, in vitro. Okay. Then in vivo, long-term implantable. Short-term invasive. Similarly, in vitro, single shot, multi-analysis. Similarly, if you take it non-clinical, single analysis, reactive monitoring, environmental bioagent. So this is the exact categorization of biosensors, clinically as well as non-clinically. Yeah, the biosensor are also applied for, agricultural industry as well as food industry. Okay, these are all the other industries are more dependent on biosensors. Yeah, now you just look at this particular small images. The global scenario usage of biosensors, pathogen detectors, toxin detector using smartphone app, e-tag, handy e-tag, then calorie counter, then similarly, you look at here bedside based at medical emergency situation in medical labs for home-based Medicare system. This is what I said. For this kind of home-based medical system, we mostly nowadays we all prefer to go for wearable technology or wearable systems. Yeah, here you just see wearable biosensors, ring sensor, smart sensor. Even the person keeps completely biosensor. Biosensor based jackets through which they are able to measure the physiological parameters. Here, if you look at DNA capture element instrument, glucometer for measurement of glucose in blood. So these are all things we could be able to. Yeah, this pregnancy test and the infectious disease biosensor, these are all things quite normally we are using. Even this is equivalent to monitoring the alcohol consumption detection, which is used by the police people. Okay. Yeah. So until then, we have discussed then biosensors, fundamentals, category, all these things now we discussed. Okay. Uh, so now let us talk about biosignal processing. Prior to that, just I would like to know, Madam, shall we continue or do you want to have any break or something like that?
Sir, you can continue, sir.
We can continue. Okay, fine, madam, fine.
Yes, sir.
What is that? What is the, closing timer?
11 o'clock, sir. Up to 11, you can take it, sir.
Okay, up to 11. That means I'll do one
will,
thing. Okay. I'll do one thing. I'll just rush up these things because biosignals and all we know very well. So I'll just skip this particular part. I'll go to the projects what we discussed because few projects I wanted to, research work what we carried out in our laboratories as well as those things, and I will discuss with you. So let me skip these things. Okay, these are all things very fundamental things we know very well. So I'll just skip all these things. Okay. Yeah. This is one of the, topic. We all know EGG signal. See, the EGG signal, electrogastogram signals, mainly used to analyze any kind of disorders in the stomach. So in this, here, we use analysis of EGG signals for digestive system disorders using neural networks. This is one of the simple work what we carried out. For this, we received fund also, as well as we put up a small center in our institute. Simply, as I said, the electrogastogram is used to analyze the, non-invasive methodology to understand the certain problems in the stomach. Okay. So for that, we need to acquire the stomach signal by placing the electrode on these areas, channel 1, channel 2, channel 3, channel 4. These areas we are placing the electrode in the abdomen part. And then from where we are acquiring the gastrogram signals, and then we are going to analyze with the neural network and other intelligent systems. And then we are going to understand what is the problem, and then what sort of further study or diagnose methodology is required. You may ask me, sir, why do you do the preliminary study and then you are going for subsequent diagnosis? Of course, really endoscopy methodology, it is little bit tedious, and then it is really invasive technique. The patients felt very more discomfort when compared with this technology. Even sometimes the doctors or gastroenterologists, they say that if based upon their knowledge base as well as the expertise level, they could be able to decide, yes, this itself is sufficient for them to provide the appropriate treatment. If it is really high serious, then only they suggest to go for endoscopy as well as subsequent procedures. So it is one of the important system in human physiology. Here, stomach plays a major role. So as I said, esophagus, duodenum, small intestine, up to large intestine, which could be easily analyzed. Okay. Let me skip all these things. Okay, mainly the gastric motility disorders, dyspepsia, nausea, vomiting and abdominal pain, ulcers. Okay, these all things are analyzed with this particular system. Here we are using, yeah, these are all the endoscope. This is a difference. Let me skip this because already I said that. Okay. Mainly this plays the electrode and then we are acquiring. So if you look at here, this particular signals, so actually the signal, the diagram got moved here from here to here. Actually before filtering, this is the signal. Okay, this is the before filtering signal. This is the after filtering signal. Okay. Okay, if you look at here, as we discussed, the electrodes are placed in the regions, and then that has been integrated with the instrumentation amplifier, and then other amplifier system. Then these are all the high pass and low pass filter circuits have been done. Then we acquire the corresponding signal. And then this is the system completely. The circuit is being made by us. Okay, this is the circuit, entire circuit. Okay, the electrodes are placed on the surface of the abdomen region. You look at here, our team members, they are placing the electrodes, and then they acquire the system. Here, initially we started with the signals acquired, and then we analyzed. Then later we integrate with the, in terms of LabVIEW and MATLAB software analysis we have done. Okay, so the mean age here is, and then male, female cases. Okay, so stomach ulcer, normal and normal individuals like this, dyspepsia as well as stomach ulcer, normal individual. These are all the various number of patients we have studied in the hospitals, and these are all the signals we acquired. So recorded EGG-A, and then for normal individuals, the V diagram which shows the dyspepsia patient, and then the next image which indicates the ulcer patients. So based on that, we are able to study whether the persons having any kind of disease like this, dyspepsia, nausea, ulcer. So the preliminary study in a non-invasive methodology, we are able to understand, and then this is the setup we have done. And then these are all the various data acquired with the data scope. Okay, and then which has been plotted into signals, and then we are using the signal spectral density estimator to estimate the value, and then whether they are having what kind of problem. Okay. So you now see here the signal for dyspepsia, how we have got it. Okay, so this amplitude level, frequency, all these stuffs we have calculated. Okay. And then gastritis, next level. So likewise, we calculated, we estimated, and then we are adopting adaptive resonance ART network as well as the LVQ. to classify what sort of problem which is. Here, the classification indicate the dyspepsia patient wave pattern as well as nausea wave pattern, vomiting pattern. Like this, we are able to normal, dyspepsia, nausea, and vomiting patterns. We are able to classify, and then we could say the person's having this kind of issue, and then what is the classification rate, what is the effectiveness of this particular technology, what we apply. All these steps we have analyzed, and then we are able to say this is what the problem. So now this is the fundamental study we have done. Next level, what we thought is, with this, can we able to provide any kind of therapy? That is what integrate both the things. Earlier work as well as this work, we received fund from DST to develop this tool. So rehabilitation tool for gastroparesis by the analysis of intestinal cells of Quachan. This, excuse me. Okay. So here, gastroparesis is a disease, okay, which doesn't have proper, motility happen in the food path or digestive tract. Okay, so what will happen is the gastric electrical stimulation, okay, is not correct. What the gastric pacemaker region. So if it is not functioning properly, the gastric pacemaker region, then obviously that leads to gastroparesis. So this, for this, they are going to provide the therapy, that is Yentra therapy. Okay. For this, again, it is really little difficult. For this, what will happen is gastric stimulator and then gastric electrogastric. So from EGG, they assess the mobility. If there is a problem, then based your controller or microcontroller or microprocessor system that computes what level of gastric stimulation to be offered to the region, stomach region. Okay, that much level of impulse is going to be delivered to that particular region. So here, if you it is a technique used to record electrical activity of the stomach and then interstitial cells of Kajal. So with this only, we are going to analyze, and then we are going to deliver the pulses, electrical signal to the stomach region. Okay. So here, if you look at the gastroparesis. Okay. So here the gastroparesis region, you look at here, okay, they are having some kind of nausea or bloating, this kind of problem may occur for them. So we have to provide stimulus in this region, okay, to alleviate the patients from that discomforts. Okay, now in this, here you just see here, there are, again, excuse me. There is a real-time signals we acquire. With that, we analyze. They are having any problem. Okay, what sort of problem they are having. Accordingly, the system what we developed, that will estimates. You just you just look at here the person's normal person. 2.5 to 4 cycles per minute. For gastroparesis patients, we are getting the cycles in terms of 2 cycles per minute. So this is where we classify that particular person's having gastroparesis. So for that, the amplitude again of EGG signal 100 to 400 microvolt, but the frequency again, which is 0.01 to 0.1 hertz. Ideal frequency is 0.03 to 0.07 hertz. So based on that, we are estimating, yes, this is what the level of gastroparesis for that patient, and then what intensity level to be delivered to the patient as a stimulus. That we estimate, and then accordingly we are going to deliver the pulses to the stomach region. Okay, these are all the various hardware part which is involved along with that circuitry. Yeah, this is the yes. EGG input signal processing PIC microcontroller. If the input signal has greater than 3 cycles per minute, yes. If the input signal has greater than 5 cycles per minute, then that is normal. If it is no, then actually, if this is the case, then a simple medication only be provided for this kind of symptoms like nausea, bloating, or any other kind of symptoms. Okay, but if the signals is less than 3 cycles per minute, or if the signal is less than 2 cycles per minute, then the gastric stimulation is going to be provided. So this gastric stimulation, we have to estimate appropriately, and then which intensity to be provided. Actually, for this, we just fix the intensity. This is again, even though it's an open forum, I wanted to convey to every one of you. If you are somebody of any of you are interested to develop any work, this is where we keep the future. Like, see, we have estimated, this is what the intensity level, we have to deliver it as a pulse. This is what the frequency level is going to fix it. But this we need to compute with intelligent systems. We need to assess what is the level, how much intensity level to be modified. So now this area has the opening to do your research in terms of the dynamic pulse or dynamic intensity level of to be delivered to that particular location of the electron. Okay, that we have to think about it. Okay. This still it's open. That's what I said. Already we have developed the circuitry. We are able to deliver the gastric pacemaker, but still it should have the intelligent system. It should be intelligent to deliver a dynamic supply to be delivered. So that is the part. Still we are able to take up the work, and then we can take it to the next level. Of course, we already discussed. Some of the students and faculty members are working on that part, but it is not yet completed. So there's an opening. That's why I'm telling you, even though it's an opening for open forum. Okay. Yeah, here it's a simulator circuit. And then what are all the various circuits we used? So you just see here, these are all the circuit very simply we made by our laboratories. With this we placed, and then we have tested. Okay. How much you just see here, the figure is a plot normal person's electrogastrogram in a digital storage oscilloscope showing 3 cycles per minute. Okay. And the stimulator provides the stimulation 14 Hertz with an onset of the trigger from EGG modules. Okay. So if it is a normal rhythm comes, obviously that indicates no stimulation. Okay. You just see a stimulation 14 Hertz. Everything will be displayed. Everything we are able to assess. Okay. And then the treatment provided by this proposed work is to improve stomach valve's effectiveness without inappropriate stimulation. Okay. Okay, this is what I said. We have received fund 5 lakhs, and then cash award also we have received. Okay. Then next thing is, I think, what's the time now? Okay. Another 5 minutes. I'll just skip this presentation also, because this also we have received a fund of around 1.5 lakhs for developing this module to find the accident victims who are who are having a different or highly serious or critical physiological parameter, the people who are the victims in the accident environment. Okay, for that also we have done some work. This is the flow. Actually, here I will just explain you that alone. See, there is a this chart, and the once to start your engine of the car, we need to ensure that the seat belt must be wear. If the seat belt wear, then only the engine will start. Then wearing status, if it is not wear, then immediately the seat belt indication will be switched on. Once wear the seat belt, then only the vehicle engine will be on. Once there is accident took place, immediately this excuse me, accident detection sensor will detect, and then it will wait for 30 seconds whether the patient is going to give any kind of input or not. If they give any input, then there won't be any response, no communication. If there is no response from the victims, then that will be get triggered, and then that will collect, GPS location, heart rate, and then heart rate as well as the actually heart rate and beat sensor that will measure. Then similarly body temperature, then coma stage detection system. All these sensors are integrated along with the seat belt. Apart from that, something is integrated in the seats of the passengers. So what will happen is, once any this kind of environment exposed, immediately that will be analyzed, and then the data will be transferred. The GPS location will sense that GPS location. Heart rate will measure and sends the parameter. Similarly, body temperature also will be sent. And then generally, if a person caught in coma stage, and then if it is persists beyond 15 to 20 minutes, then they may be completely, they may be exposed to brain damage. To avoid that, this particular unit will trigger a small pricking module, with a small needle that pricks the person to make them awake. So this kind of methodology only we provided. Actually, these are all the things which is not, nobody has done it. For this, actually, this particular technology has been taken over by the Mahindra Satyam, okay, for developing and then putting it in their unit. Okay, this kind of thing already we have done. Okay, yeah, these are all the outcomes. Okay, now let me go to another unit. Actually, yeah, let me skip this because this is the apnea monitor. This also we were working. Actually, I'll just skip this because I'll go to another important thing. Yeah, Parkinson's, this is also we were working. I wanted to show you only one thing before concluding. Yeah, this is the one. Actually, when I was 2018, I think so, I went to IISc Bangalore for a hackathon, medical device development hackathon. Here, this is myself, Prabhakar, and then this is the, who is the research scholar at IISc Bangalore, who is the designer, and this fellow is the mentor, and then this is also Jyotilal, who is also a mentor. He is the person, a doctor who is working in Apollo Hospital, Bangalore, and then she is also an engineer from IIT Kanpur. Okay, the thing is, see, we wanted to develop, vector knee. This is the name we have delivered, but actually speaking, while doing the knee replacement surgery, the doctors have to use this particular module, which is working based upon the accelerometer and gyroscope principle. So here they need to fix the, actually you just look at the, bones. If it is a normal person, this is very straight. Okay. If the persons who are having arthritis, the bones get bent. At that time, the doctors will do how much bend took place. Accordingly, they will assess, and then they will cut the bone in the top and then bottom, and then they will do make this particular bone structure in a straight one. So this is the thing. Actually, within we were attended this particular program for 4 days. I thought within the 4 days, what could be able to deliver or what could be able to develop. But when I was started, I had such a thought. But when we, closed on the 4th day, I was wondered, yeah, because we were able to provide a solution as with the models, different models, really, which was a good experience for me as well as everyone who took part with that particular event. Why I'm telling you this is, the doctor said that For this particular, thing, unit, they need to make a drill in this location. They have to insert a rod kind of thing. With that, they will position. They are going to align this bone, okay, and then another lower bone. Both the bones they are going to align it based with using this unit. The cost of this particular module itself is 1.5 lakhs. So he said the entire unit as well as the sensor system, the sensor module, smart sensor module, which maximum developmental cost may be around 20 to 25,000. That's it. Okay. Maybe maximum we can sell it for the entire cost maybe 1,500 rupees, but we are able to deliver at the cost of 25,000 or 30,000. That is sufficient. That is enough. But the company people who are delivering it right now, they are imported somewhere, and then which is sold for something around 1.5 lakhs. But this is used only for one time. Once they use it for one patient, they have to throw it. Okay. So this kind of difficulties he put forward to us to find a solution. Okay. So for that, the same kind of methodology we have applied, and then we are able to study, and then we develop this kind of models. You just see here, this is the bone structures we developed. He is also holding one bone kind of thing, and these are all the units what we proposed. Okay, small units we have developed because they have full facilities. This is the design. These are all the diagrams. After discussion, we draw and develop the diagrams for making the product. Okay. So with this here, you just look at this particular thing. You are able to understand how we are trying to make this. Are you able to see this video kind of thing? Yeah.
Yes, sir.
Okay. So now I think you are able to understand. The main thing is this is the unit which is going to align, okay, align both the bones, and then here there is a piece which provides the physicians to make the bone to cut the exact level. Okay, even they are going to cut for okay, 1 or 2 mm. Accordingly, they are able to adjust, and then that kind of support which could be able to provide. That is one thing. And then there are 2 ligaments, this side and then the opposite another side. This ligaments also to be adjusted. How? Based upon the pressure sensor what we place between both the bones, that will assess. Oh, this is the excuse me. This is the tension, and then this is the pressure level is to be applied. Accordingly, what they will do here also, the tendons and ligaments are also be adjusted. Okay, then only the person able to get a completely, instead of bent knee, they are going to have a straight knee. So this particular module is highly important or essential. Still, there is a requirement for this, because this work is taken care, still it is under development at AAC. Even just 10 days back, I spoke to the doctor. He said, Professor, still the work is under development, still the work is going on. Why I'm telling you this forum is, it's a kind of, real requirement for the doctors by the biomedical engineers. Okay, from our side, we need to support something to the physicians based upon their requirements. Okay, so with this, I think actually we have estimated here again. We concluded that particular product we are able to deliver the cost of 15,000. We are able to provide this particular device. Maybe even though it's a use and throw kind of thing, which come into the reality, that is far better, because the cost right now, which is there in the market, is 1.5 lakhs. If we are able to provide it for 15,000 or 20,000, it is almost 10 times which comes down the cost. So that is very important and crucial and requirement. Okay. So with this, I'll conclude my session. Thanks for the opportunity. Thank you. Okay.
Thank you, sir.
Thank
Participants, any queries?
Whatever the standard chart that you are giving for the ECG for a human being, that is differ with respect to the age factor.
Pardon, sir, I may not be able to get you.
Standard chart, parameter standard chart for human being, that is different with respect to the age factor.
Yes, of course.
Because you cannot show that that is in standard chart, that in your slide there is no age matter is there. So that is differ with respect to the age factor.
No, which slide you are talking about? ECG we are not at. Actually, we are not.
Yeah.
Okay, ECG. Yeah. Yes.
That is differ with respect to the age.
No. Actually, we have not considered that. But of course, there is a difference with the age. Actually, that part, that's what I said. Certain part we have not yet. That is left open. Okay.
Okay.
Actually,
and whatever which solution that we use for the fixation of electrode with skin.
Pardon? Hello? Which?
To fix the electrode with skin, which solution is used for electrode, bioelectrode?
For electrode, in the sense, are you talking about in terms of position? Okay.
For sensing, that electrode is used for sensing the parameter of the body. Okay, in case of ECG or in case of EEG or whatever the instrument that we use. So which solution is used? Any solution is.
Solution in the sense, are you talking about in terms of gel, what we apply?
Gel.
Yeah, gel we are applying. Yes, we apply gel over the surface of the skin. Okay, after that only we place the electrode. Okay, that is how we place.
Thank you, sir.
Okay, thank you.
Sir, my side one question.
Tell me, ma'am.
It is actually EGG signal is in terms of microvolts only, sir.
Correct.
So if obese person is going to get EGG, there must be a
yes, of course.
Getting that EGG. That's why I'm asking. All the patients can go for the EGG, or they are advised to go for some other tests?
Yes, ma'am. Of course, the basic. It's mainly the thing is, EGG for non-invasive methodology. Okay.
Yes.
As you asked, if the person is highly obese, sometimes the EGG signal may not be appropriate. For that, whatever the circuit which we develop now, still which has to be improved. But of course, as you said, there may be some kind of deviations with the regular, normal EGG or the pattern what we acquire. Okay. In that case, of course, sometimes what we suggested is better to go for endoscopy. If see the subsequent study, we generally we have to suggest to go for endoscopy. Since it's a preliminary study, we prefer to go for EGG. And then, as I said, if there is a gastroparesis kind of thing, we may not deliver the gastric pacemaker or pulses directly to the stomach. It is really difficult task. For that, the procedure is again different. Either we need to take up the needle electrode kind of thing. After that only we can deliver to the particular location of the stomach. See, it's a procedure. It's a clinical procedure involved along with that. The person supposed to be in the theater. Then only they can do all those stuffs. To avoid that only, we are going to provide the electrode on the surface of the screen, and then again that is going to be placed on the stomach region. Okay, that is how we plan. It's purely it's vary for person to person. We are providing a solution. The physicians only at an outset, the physician also decide, yes, whether it is applicable for that particular obese person or not. If it is not completely suitable for them, they have to take care of complete clinical procedures only.
Sir, is there any trained person is needed to fix the electrodes, sir, to acquire EGG?
No, madam. Generally, we have seen that locations. I have shown that locations. Few locations is right. Yeah.
Yes, sir.
These are all the locations. You look at this particular image. Maybe there may be little bit deviations may come. Maybe few amounts can change. Okay. But general acquisition, this is what the regions. Okay. This is where the regions we supposed to place the electron. Are you able to see the screen?
Yes, sir. Yes, sir.
Okay. So these are the general regions we have to use, and then see now here you just exactly you are able to see that. Okay.
So the electrode is same as that of acquiring ECG, sir, or it is?
Yeah. Yes. We have used the similar electrodes only. Okay. Actually, here also that's what I said. Few suggestions when we presented to the few experts in DST. They suggested, why don't you go for some kind of micro needle electrodes? Okay. So through which you are able to get highly precise signal out of it, but we don't know how much which is suitable. And then again, there should be some kind of subsequent study we need to carry out.
Okay.
Yes.
Thank you, sir.
Okay. Any other discussions?
Any other queries from the participant side? Unmute yourself and ask queries, or you can make your queries in the chat box. Okay. There is no question, sir. Pradeep, sir.
Yes, ma'am. I will proceed.
Okay.
Good morning, participants. Myself, K. Pradeep, Assistant Professor, Biomedical Engineering Department, PSNCT. It is indeed a great pleasure for me to propose a vote of thanks for session 1 today. On behalf of Department of BME, PSNCT, I'd like to thank Dr. S. Prabhakar sir, Director Research and Head of the Department, Biomedical Engineering, Dr. NGP Institute of Technology, Coimbatore. Today's topic was more relevant in current trend of biomedical engineering field. I hope participants learn about more biosensors and technology involved in design of biosensors. And it was very interesting and curious about your case studies, sir. I think your case studies will made a spark for the participants, so those who are yet to start their research field. So thank you so much, sir, for accepting our invitation in your busy schedule.
Thank you.
Thank you, sir. Thank you, sir. Thank you so much. Participants, next session will start by 11:30. So we'll be having a 10 minutes break. So exactly by 11:30, we shall start next session. on the same link. Thank you.
Thank you. Thank you.
Thank you
Thank
very
you.
much. Thank you,
Thank
sir.
you. Thank you. Thanks for the participation.
Thanks. Ma'am, am I audible, ma'am?
Yes, ma'am.
Okay.
Yes, ma'am. You're audible.
Yes, yes. Good afternoon, all. It gives me immense pleasure to invite a guest speaker of this session, Mr. Jagaisu, works as a senior application engineer at Integrated Microsystem, Gurgaon. He has been working on several EDA, CAD tools, computational modeling, and simulation tools from the past 6 years and has gained expertise simpleware software from Synopsys. He looks over the technical support for this software and closely works with simpleware customers to help them with their designing and modeling needs. Another part of his work is to provide training to existing customers and demonstrations to various institutes and faculties who are working in the field of medical image processing, patient-specific implant design, surgical planning, 3D printing, and in material modeling, manufacturing, and simulation. One more speaker, I welcome one more speaker, Mr. Pradeep, and he works as an application engineer at Integrated Microsystem Gurgaon. Has been working on several medical image processing softwares, FE, CFD, and CAD tools, material modeling and simulation tools from the past 3 years, and gained expertise in the simpleware software from Synopsys. And he also looks over the technical support for this software and closely works with simpleware customers to help them with their designing and modeling needs. Another part of his job is to provide demonstrations to various institutes and faculties who are working in the field of medical image processing, patient-specific implant designs, surgical planning, 3D printing, and in material modeling, manufacturing, and simulation. This a small intro. I hand over the session to Jagaisu and Mr. Jagaisu and Pradeep. Welcome, sir.
Thank you very much, ma'am. Thank you very much for your introduction. So today's presentation will be done by my colleague Pradeep, and he is already presenting and is present here. So Pradeep, okay, you can carry on.
Yes, sir. Yes.
Okay, very good morning to all of you, and I would like to thank PSNA College and BME department and all faculty members. So just before going to start with this online session, as ma'am already introduced me and my colleague, and we are based in Gurgaon, India, and we are the authorized distributor of this Synopsys simpleware software for sales and support in India. And so let's start this online session. Okay. Okay, so first I will start by giving the basic idea about the medical image processing system. Like I will tell you that what is medical image processing and what are the benefits of medical image processing and how does medical image processing work. After that, we will deal with the software and some case studies, and after that, we will show you some a live demonstration of the software. And after that, if anyone have any query related to this online session, so you can post your query or you can ask by unmuting yourself. Okay. So the basic medical image processing system consists of these steps. Like first step is acquisition, and after that processing. Okay, so acquisition means, let's say, the medical image processing. But if I told you about that, what is medical image processing? So medical image processing encompasses the use of exploration of 3D image data sets of human body, obtained most commonly from computed tomography, CT, or we can say MRI scanner, to diagnose the pathologies, or to guide for surgical planning and for research purpose. Medical image processing also carried out by radiologists and engineers, and for the better understand the anatomies of either individual patients or we can say a group. Okay, and that after this processing step consists of these several steps. The first is pre-processing. After that, segmentation, and then detection, and then analyzing or results. After that, diagnosis, that is done by the doctor or clinician. Okay, and this part is we can say carried out in this simpleware software. And after that, if you want to visualize or want to print a report or anything, that you can also prepare in that software. So let's say if I give you the idea, like what are the benefits of medical image processing. We can say the main benefits of medical image processing is that it allows for in-depth but non-invasive exploration of internal anatomy. 3D models of the anatomies of interest can be created, and studies to improve treatment outcomes for the patient. Or we can improve medical devices and drug delivery system, or achieve more informed diagnosis. It has become one of the key tool leverages for medical advancement in recent years. And let's say if I told you about how does medical image processing work. Okay, and the process of medical image processing began by acquiring the raw data, that is from CT or MRI data. This process is, you can say, acquisition of the images, and reconstructing them into a format suitable for use in relevant software. A 3D bitmap of grayscale intensities containing a voxel 3D pixel, let's say, a create means a grid create the typical input for image processing. After, we can say, a CT scan, a grayscale intensity depend on X-ray absorption, while in MRI it is determined by the strength of signal from proton particle during relaxation and after application of very strong magnetic field. Or we can say, let's say, this medical image processing operation at the 2D and 3D level includes reducing and removing the unwanted noise and artifacts of image filters. Okay, let's say so now if I tell you about the simpleware software. So simpleware software is a 3D image processing and model generation software program that is developed by the Synopsys for visualize, analyze, quantify, segment and export 3D image data from micro CT or MRI, CT, and X-ray and other modality for CAD, FEA, CFD, and 3D printing applications. The software is used in the life sciences, or we can say material sciences, non-destructive testing, reverse engineering, and petrophysics for oil and gas field. Okay. So by seeing this picture, you can get an idea that what kind of work we are going to by using this simpleware software. So first we acquire the MRI or CT images. After that, we convert a 3D model, place some landmarks, and after that we can customize, we can measure, we can segment, we can quantify, and then export into STL file for 3D printing application. After that, we can also remesh or create a FE or CFD meshes of any anatomies in this. And these are some of the supports and supported import and export file format by this simpleware software. So ScanIP is the base module. Like Over here, we can see that these are the some import formats supported by this software. It supports various image dataset, DICOM text, DICOM-D, industrial related image, raw data images, and 2D image stack in these formats. After that, we also support some pixel types, or we have a variety of export format supports supported by this software. After that, also finite element export formats. You can export in these formats. You can export in Abacus, Adena, ANSYS, ANSYS Workbench, COMSOL, MATLAB, VTK, Pattern, Neston, Fluent. There are various formats available for export these, or we can say our project into some leading specific solvers for the simulation purpose. Okay. If we discuss about the application area, like you can use this in life sciences and clinical application, materials and manufacturing field. If we discuss about the application in orthopedic field, like in life sciences and clinical application, the first is orthopedic for accurate anatomical model, and we can say for we can use the simple way in orthopedic for medical image segmentation and for to gain insight into patient specific implant. After that, for product design analysis, we also have option for biomechanics for consumer product. On the later slide, I will discuss in more detail about the application area where we can analyze or we can utilize the software. Okay. So physiological flow for cardiovascular and respiratory system, and electromagnetic and neuromodulation for human body models for simulation. After we have option for medical device research and development for image integration with the any device, or 3D printing preparation for export as a high quality STL file for 3D printing application. We also have some application in complex material modeling, digital rock physics, non-destructive evaluation, inspection and metrology, reverse engineering and additive manufacturing. Let's say if I discuss, because we are going to focus only on that part, how you can analyze this in for life sciences. The first is orthopedic. Like we can use simple way in orthopedic research area for medical image segmentation, medical image processing, and model generation for orthopedic applications to gain insight into patient-specific implant design. This saves times with the 3D medical imaging software and for exploring the design and simulating real-world scenarios. After that, we have this product design and analysis. You can design any your customize your design for according to individual anatomic need for the customer. We also have some options for export models to simulate real-world performance. After that, we can discuss about the physiological flow. Yes, that is for cardiovascular and respiratory system. And today we are going to discuss on that part more. Okay. So you can quantify vessel with the central line network tool to see the cross section at a particular location, or to see the flow of blood through the veins. Or you can create your finite element mesh or CFD mesh in this. Okay. If let's discuss about the electromagnetic and neuromodulation. So that is for non-invasive direct current simulation and brain temporal interference study for human body models for simulation. Like you can create, or you can create your phantom like model for integrate CAD design like MRI coils or electrode with the image dataset. Yes, and you are. It is very easy to use a registration tool for positioning device. Let's say implant with the image dataset, and you can generate and export simulation ready meshes, or you can also have an option for remesh any particular image. We also have application in medical device research and development for device and image integration. Already discussed about that, like how you can rapidly integrate with your image. We can say MRI or CT scan with your CAD file. We have another option for 3D printing preparation. Like you can generate your surface model You can customize your surface model. You can give internal structure to your any specific anatomies, or you can, after that, you can you also have an option for giving the cell thickness. Then you can export your STL file for 3D printing purpose. If you want to print that model for teaching purpose, then you can print that 3D model, and then you can do any kind of measurement or study on that particular anatomy. So now we are going to discuss about the simpleware case studies. I will show you some customers who use this simpleware software in the research area. So we will discuss about some of the applications, like how some customer uses this simpleware software. So first I will begin by this case study one. So that is 3D numerical foot model for running shoe design. That is also a simpleware case study. So let's start. Okay. So as we all know that the 3D modeling and simulation saves time, cost, and material. Okay. So ASICS is a company that use 3D computational models to better understand the role of stability in running shoe. Optimizing the simulation reduces the risk of lower extremity injuries or for runners, as well as enhancing the performance, sole structures, or you can say the heel eversion angle, and particularly important for understanding the stability. Or let's say if I said alongside the experimental method, the model created, yes, the model created in simpleware software for export to Abacus simulation tool helps ASICS reduce prototyping type. We can say it reduces the prototyping time and cost, as well as the manufacturing waste. So if I discuss about the characteristic, we can say what are the characteristics it used, or if I discuss about like how this simpleware software generate a foot model for that particular research. So this particular diagram showing the heterogeneous numerical model considering the soft tissue. Here these are the soft tissue, and the bone, cartilage, ligaments, and plantar and fascia. Okay. So the characteristics include like it include highly accurate multi-part 3D foot model that is generated in the simpleware software by using the scan IP based module from a CT dataset. After that, they prepare a finite element mesh of that part, and after that, export to Abacus used for the predict to sole stability. After that, ASICS successfully updated the sole design to improve the customer performance. And this techniques helps ASICS reduce prototyping time and cost, as well as manufacturing cost. So this part is done by the simpleware software for the segmentation of that cartilage, plantar fascia, soft tissue, and bone. Let's say if I told you, if I give you an idea about how you can generate or you can create a foot model in simpleware software. Let's say to predict the sole stability, scan of foot for a healthy person was obtained using a X-ray computed tomography, and the image data was imported to simpleware scan IP software to build a 3D model prior to the generation of a finite element model representing different parts of the foot, like soft tissue, bones, cartilage, ligament, and plantar fascia. The details of the model enable ASICS to be confident in the accuracy of their anatomical simulation. So these steps are showing that how you can convert or you can segment, reconstruct, and can generate FE model for simulation purpose. So this image is showing the foot MRI CT scan images, a sample. Or after that, we do the segmentation of foot region in this simpleware software. After that, we prepare a 3D reconstruction, and then we have options to export in 3D printing application or for finite element model generation for simulation purpose. Okay. After that, for simulating the SU performance, so after the creation of finite element mesh in this Impalware software, so our next step is to simulating the SU performance. So the Simpleware export in the Abacus was used to with the model to calculate the deformation modes on polymer foam sheet. This sheet. This picture showing before loading and after loading. Let's say, and as I already told you that Abacus was used with the model to calculate the deformation mode. You can say the deformation modes on polymer foam sheets with 3 types of hardness. After that we can say the result shows good agreement with the experimental testing. Validation simulation as a way of enhancing the existing ASICS method. The numerical model was confirmed to accurately predict the sole stability. We can say the leading ASICS to successfully update the design of their soles to improve the performance of customers, we can say. So this picture is showing that the medial and lateral of a foot design. We have created a finite element mesh in the Simpleware software. And the heel inversion calculated by the proposed model corresponding to foot flat phase. This picture is showing that the heel inversion calculated by the proposed model. After that, the motion capture system with force plate to measure the heel inversion shoe angle. So you can say the show stability parameter. This picture is in the, we can capture the motion system with force plate to measure heel angle. Okay, so after that there is some conclusion like what they have concluded. So ASICS have successfully created an accurate, highly optimized model tailored to specific running condition. The model is therefore valuable for shoe stability design, reducing the prototyping cost and time, and skipping the practical prototyping to improve the sustainability. A product have been introduced as a practical designing example with the research contributing to an improved, we can say, understanding of running shoe stability and reducing the excessive foot joint motion or production during the contact phase in running. As you all are aware that we can design according to your need, and then you can export in any of your leading solver for simulation purpose. Okay. After that, we would like to thank these. We have taken the reference from these. Okay. So our next case study is torso model generation for simulating pacemaker performance. Okay, so this is also a simple case study, a torso model generation for simulating the pacemaker performance. So Microport is a company that develop life-saving medical product for patients around the world. One of the Microport specialty in the manufacturing cardiac rhythm management devices, that is CRM, for testing cardiac rhythm disorder and heart failure. This company uses the Simpleware software for, we can say, to model the complex pacemaker geometry to better understand patient therapies for conditions such as bradycardia and tachycardia. And after that, image-based finite element, you can say FE simulation, offers an alternative testing method for them to reduce the reliance on animal testing, cut the risk of device failure, and also provide the insight without the same ethical hazards as animal testing. Okay. After that, he started by doing their project in this Simpleware software, but they were started by using this software. The first step they taken processing a torso model, how they can process actually. Okay. As we all know that the simulation of human body model reducing the need for animal testing. As we know that simulation is fast, efficient, and less expensive. Okay, so they use a simpleware software to be repaired for the meshing. They have imported the data set for remeshing. So Microport began their simulation process with a realistic geometry developed from a data set available in their foundation, and and then after that they use simpleware software to process the original STL and segmented region of interest for simulation. Actually, and the easy of use simpleware software enables them to fix fix the errors such as like holes. These are errors like holes, vertex and vertex connection, and known manifold edges. Actually, they imported that project again into the simpleware software and then reduce some errors, like if there is any holes or vertex connections, and there is if there is any known manifold edges, so they can remesh that surface for the processing in simpleware, and then made the STL data suitable for meshing and simulation. After this, they create a FE model for simulation purpose. So once the data was segmented in the simpleware software, then they export that data for simulation purpose. They export that FE data from the simpleware software for console multiphysics export, and export IGS files for geometry editing and remeshing purpose. So the simpleware guaranteed that their meshes are watertight with smooth, accurate geometries and correct topologies without any gap. Okay, so this level of quality makes the meshes ready for electromagnetic simulation in console multiphysics. So this picture is showing that simpleware software, you can say the mesh quality, there is no gap, and actually it is a very watertight. So we imported this data set into console software for multiphysics analysis, for we can say electromagnetic analysis. After that, generating the human heart model in this simpleware software. So we have also generated a human heart model by using this software. So to improve the detail of simulation, a simpleware software was used to process a heart model created from a separate data set. Yes, the main task of this data set was to add the chambers and add the chamber to the original heart model with image processing tools such as probe, segmentation, threshold, paint, range, etc. And they use these tools to remove the unnecessary details from the image data. And after that, they perform the segmentation of the chambers and the closing of the outer surface of the model to a solid. This allowed individual nerves file to be exported from a simpleware software into console. So this picture is showing that close outer surface of a solid and then segment chamber generate individual NURBS model of each part. Okay, so they have segmented that heart model and then created a NURBS model. NURBS, so we can say non-uniform rational B-spline. Okay, so after that, they exported into the console for multiphysics analysis. After that, they go for electromagnetic simulation. As I already told you about, the simpleware meshes are used in the console multiphysics to test the placement of electrode within the body and the tissue conductivity when applying the voltage. Because we are discussing the torso motor generation for simulating the pacemaker performance. Yes, and when applying the voltage, the output was the current pathway and the electric field inside the heart. The simulation results were compared with the literature and demonstrated a deviation error between 7 to 20% of expected result, and depending upon their configuration that they have prepared. Okay, so this picture showing that the pathways of electric field and current density in console multiphysics, because they have imported the data set from simple software to COMSOL multiphysics for electric field analysis. So over here we can see the current density normalization starting from this range to this. And then later I will show you how you can convert, you can create your model by using this software, and then you can create your finite element mesh, CFT mesh, surface model, NURBS, etc. Okay. So after that, they have concluded some results. The FE model was suitable for comparing the different device anatomic configuration to determine which configuration is better. Because as we have tested many models, so the model can be determined the optimal optimal position of the electrode and optimal pathways to maintain the defibrillation at an acceptable level to both simplify the implant procedure and deliver the patient comfort, because the comfort is the main aim. By using these techniques, this allow a microport company to reduce their reliance on costly animal tests and improve efficiency and accuracy of their work, because this is a very severe, we can say, they require that urgently, so they prepare that and resolve their. After that, if we discuss about the case study 3, so case study 3 is variability and accuracy of spine segmentation. Okay, so we are going to discuss about the variability and accuracy of spine segmentation, because we have imported this CT MRI of this, we can say CT of human body for the segmentation of spine. Okay. So if I give you the overview, like patient-specific computation model of bony atomic take from medical CT imaging offer a significant advances for biomechanics research, because there are various research field available in biomechanics research field. So okay, so these include the ability to perform non-invasive investigation of joint mechanics and interaction between medical device and human body model using the finite element module that are also available in the simpler software. This study involved the testing and the effectiveness of manual segmentation, because the manual segmentation is the time consuming, and we can say the okay. So this study involved testing and effectiveness of manual segmentation of lumbar vertebrae, taking into account the proximity of articulating the surfaces and degenerative joint changes. So the simpleware ScanIP that was base model was used to generate a model that is suitable for measurement analysis, and then analysis is performed in MATLAB. Okay. Actually, this picture is showing that how you can do your segmentation, and then if you want to export this spine segmented part to your 3D printing purpose, then you also have an option to convert this segmented part into a surface model. And if you want to provide any we can say internal structure, we also have an option to provide the internal structure, and then we can export this part to as a STL file for 3D printing application. Let's say if we begin with the image processing, like how they start working with that data set. So 8 cadaveric lumbar spine segments, that is T12 sacrum, were cleaned of muscles and loose connective tissue before being CT scanned. This is the machine with a slice thickness of 0.6 mm. Okay. The 3D image track were then imported to simpleware ScanIP software, that is a base model, where a custom window with as a level and as well as curvature anisotropic diffusion noise filter were applied, because without the processing we can't do the segmentation correctly. Okay, so this needs some pre-processing, so like probing filtering, and after that you can apply thresholding and flood fill tools and generation of mask of a particular anatomy, which was then segmented into individual laboratory and manually edited to deal with the connectivity across the phase joints. And after that, we have applied some morphological close filters to reduce if there is any open cavity or if there is any open holes before smoothing was carried out, and the model generated in STL format for export to MATLAB. We also have options to export in various file formats like NC Sabarkas, as I already told you in the beginning of this slide. Okay. After that, we begin with the analysis part. Okay. So because we have imported the data set into MATLAB. So once imported into MATLAB, the quality of segmentation was tested based on two observers performing the procedure twice on each specimen. So they are performing on twice on each specimen. And the intra and inter observer differences were calculated by registering the surface model with the interactive closest point algorithm. A map of the nearest neighbor distance between each model was created for each laboratory, and the distribution of their distances analyzed into this simple system. And actually, the five laboratories were then discirculated from their neighbors and clean off all the soft tissues, because we don't want to focus on the soft tissue. So that's why they clean the soft tissue and rescan and segment without adjacent laboratory and soft tissue to evaluate the original segmentation runtime. And then if you want, then you can export in your available according to your requirement. So this is the result, or we can say conclusion. So the analysis of segmented, or we can say the segmentation indicated root mean square error. So they also get some error, or the distance between the neighboring point on the registered surface, that is below 0.39 mm. For accuracy based on the comparison between the model before and after disarticulation, the 95th percentile of distances was some millimeter in all instances, as all RMS, we can say root mean square measurements from comparison of model prior to disarticulation. The test therefore demonstrated the accuracy of model generated from the CT scan of the lumbar spine in simple software, and then indicating the potential of future study involving the patient-specific modeling of the lumbar spine. So I hope this is the last case study. So modeling alternative electric field for brain tumor treatment. Then let's say if I give you the overview about the this case study for modeling electric current field for brain tumor treatment. So alternating electric field for tumor treating field, we can say TT field therapy is a type of electromagnetic field therapy to treat cancer, particularly recurrent glioblastoma. TT field therapy delivers we can say low intensity current through array on the scalp, and has demonstrated good result compared to traditional method, because traditional method is more complete. So however, the precise distribution of TT field within the brain and the extent to which they cover the recurrent glioblastoma so remains poorly understood, because computational simulation from medical image data offers a solution for analyzing the effect of TT field therapy. For the treatment of glioblastoma, simpler software were used to generate a model for this purpose. Okay, just give me a minute. After that, the first step is to image, we can say MRI image acquisition, and the tumor treatment. Because without the acquisition of image, you can't deal with the 3D model. Okay, so researchers aims to determine the frequency, a dependent electric field distribution within a patient's brain. For this, they'd use co-registered post gadolinium, a T1 weighted T2 NMP rates images. So together with a pre-specified conductivity, the relative permittivity value for the cerebral structure, retrospective neuroimaging analysis of TT field therapy in a 67-year-old female patient with a recurrent glioblastoma in the posterior right frontal vein. You can say, okay, for that 6 months after the initial treatment, and then she received both the bevacizumab infused at a dose of this, and then the placement of the transducer array was based on a personalized computer generated layout, because they have prepared that layout, which is derived from a MRI based morphometric measurements of her head, or we can see the tumor sites and the tumor location. She continued both treatment for 24 months until another site of the disease was detected in the lateral border of the right lateral ventricle. So this picture showing the tumor treatment, like MRI image of patient's brain, a 6 month. This is the 6 month after initial treatment. Now this is after initial treatment, and this lower slice, that is after 24 months, a new site of disease was detected, and at the lateral border of the right lateral ventricle, you can see here. While the primary tumor was stable. Okay, so image processing and meshing is also performed in the simple way software. Let's say from the same baseline MRI used for array layout, a 3D model of a head was generated from the co-registered MR image dataset using simpleware scan IP. Using a simpleware FE, that is also a module in the software, a finite element mesh was generated for each of the segmented head structure. They are showing, okay, including the skull, dura, cerebrospinal fluid, or we can say white or gray matters, and ventricle, brainstem, and cerebellum, and the recurrent glioblastoma, as well as the transducer array. The composite, you can say the composite finite element model was then exported as a mesh in COMSOL multiphysics format, because we have options to, we can say, configure our finite element mesh if you want to export in any of the formats. Okay, so after that they have performed some simulation results for that part for their project, because they have created a finite element mesh in the simple way software. After that they have imported that particular project in COMSOL multiphysics to solve the electric field distribution, because respective conductivity and relative permittivity values were used were 0.001, or we can say Siemens per meter. And there are some results they have tested, because over here in this image we can see the analysis of electric field in COMSOL multiphysics. High field strength is seen at the ventricle horns, and there is an inhomogeneous, you can say there is inhomogeneous electric field distribution on the tumor in this picture. You can see here the inhomogeneous electric field distribution. Or we can also see here that a neoenhancing tumor is situated at the lateral border. of the right lateral ventricle in an area with a relative lower electric field strength. You can see here. So that is the final conclusion that they have prepared. So analysis revealed valuable information on the procedure, including the location of the highest electric field strength around the ceramic disc for each array, and the potential to reduce the scalp irritations. The inhomogeneous electric field distribution was also observed on the tumor, while the MRI revealed a new enhancing tumor subsequent to treatment in a location with relatively low electric field strength. So being able to better understand the distribution of electric current using the model generated from the imaging data offers an important method for analyzing the efficiency of TT field therapies compared to conventional chemotherapies. So here is, we have some recommended system requirements. You can look over here to use that software for your particular research. Okay, so in between, if anyone have any query, so you can unmute yourself to ask the query, or you can post your query in the chat box as well. Because I'm going to discuss about the short description about the module available in the Simpleware software.
Dear participants, do you have any queries? You can unmute yourself and I ask a question.
Okay, so if I give you an idea about the basic details about the modules. So Sttp is a base module. It provides an extensive selection of image visualization, measurement, processing tools for working with the 3D image data. We can say 3D medical image data, and then you can export your segmented image as a STL file for surface meshes and point cloud to CAD packages, solvers. You can say 3D printer or for 3D printing application. This finite element, that is also a mesh module. It is used to generate a volume of surface meshes from a segmented image data, and then you can use to define contact surface, boundary condition, and the material property you can also define in that. Then you can directly import that, what you can say, export into all leading CAD packages or specific solvers. After that, this NURBS, that is also a non-uniform rational B-spline. So this facilitates the generation of NURB surfaces from the segmented image data ready for import to CAD packages. After that, this CAD, let's say if this module allow you to import and positioning of CAD model. Let's say if you have any implant and then you want that implant imported into the software, then you want to merge that implant with the image data set bound. So if you have that module, then you can import your implant and then you can do your positioning and placing of the implant with the image data set. Okay. And you can also provide internal structure for 3D printing application by using the CAD module. After that, we have a design link, that is a connect module. Design link, we can say SolidWorks connect module. So at Simpleware, design link allows user of Simpleware software and SolidWorks to harness the power of both software packages and speed up the production development workflow. This module eliminates the need to import and export between the two packages. There are some physics module for simulation purpose. For analysis, these are solid flow and Laplace. These are more related to rock physics field because these are used to calculate some effective stiffness. This solid model used to calculate some static, some effective stiffness tensor or individual elastic moduli of material sample. All these modules perform numerical homogenization with a built-in FE solver. You can say Stokes solver. This flow module can also be used to calculate the absolute permeability tensor of a porous material sample. Then this Laplace module, this can be also used to calculate the effective property of material. We can say whose behavior is governed by the Laplace equation. You can calculate your electric conductivity, permittivity, thermal conductivity, and molecular diffusivity. All these modules perform numerical homogenization with a built-in FE solver. So there we have some automated solution modules like AS Ortho for orthopedic auto segmentation. Because this provide anatomy specific automated segmentation tool for the segmentation of hip and knee region using the machine learning algorithm. And also this automatically identify the bones and some common landmarks. We have this AS cardio, that is cardiac auto segmental module. This allows you to specify automated segmentation for heart. Basically, it is also a automated module. So by using this module, you can segment or you can do your segmentation of heart within less than 2 minutes. Okay. As we know that the segmentation of heart is a very complex task. If any expert user wants to segment that part, it takes around 4 hours to do the segmentation of heart. By using AS Ortho, by using AS Cardio, you can segment that part within the 2 minutes. Then we have custom modeler, so you can create a fully customized automated solution by using a machine learning algorithm for, we can say, plug-in purpose built for customer requirements according to for their research work. So at this time, if anyone have any question, so you can ask, you can unmute yourself to ask any question related to the presentation, or then we can move to the next part of this online session, that is a live demonstration of the software, like how you can create your 3D model for specific research purpose.
Any queries, dear participants? Okay, sir, proceed, sir.
Okay. So I'm going to shift on my another screen. Okay, so my screen is visible to all of everyone can see my screen. Okay.
Yes, sir. Okay. What you shared is visible, sir.
Okay, fine, man. So as we can see here, this is the graphical user interface of Simpleware software. We also have some option for helps and supports for, let's say, and for tutorials. That if anyone wants to begin, if anyone wants to start with their research work, so you can follow some tutorials to learn about your specific requirement. For import and positioning of CAD implant, export to CFD, for segmentation, for implant positioning and placing, segmentation of heart, for spine, these are for material related, and these are for Also, you can do some quick measurements. So by following this tutorial, you will able to learn about the basic tools and features and the capabilities of the software according to your needs. And this is the simple way tool ribbon populated over the top of this GUI. On this left hand side, we can see some project information. So project information contains three tabs like geometry. It tells us about the geometrical properties, object counts like any volume or surface mass, and it tells about the applications like memory consuming. In this we have dataset browser. If you have performed any of this, if you have any mask, so your mask will be seen here. So for this live demonstration, I will start by importing a DICOM image. A DICOM image of a human body. Okay, so if I click on this, so this brings me to this import dialog. So over here, it asks me to select a scan folder, or you can, let's say if I click on this scan folder, and I have here some DICOM files. So we have a series, you can see here the preview is also available. It gives us about the DICOM file information, like about the patient name, number of images, time frame used, modality, study date, and we have options to see the slice preview to check whether we have imported a correct data set or wrong data set. So by using this slice preview, you can check your data set. We also have some option for DICOM tags. You can also anonymize your DICOM tags. By default, it anonymizes all DICOM tags. So we can see here the file name .tcm file and the pixel size, and the application size is 286. Let's say if I click on this finish, right now it is importing the old slices. Okay. So as we have imported the slice into the software, so if we look here, there are 4 views. So this is a 3D view. It gives us other information about in 3D, like how we are dealing with the 3D data. And these are some medical views, 2D slice views. That is a sagittal view, that is coronal view, and then we have a axial view. We have also options for checking the slice preview. You can also see in that coronal part also, because we are going to discuss about this pelvic region segmentation, and then we will export that particular part for 3D printing. Okay, and this is our live 3D view. If I click on this expand 3D view, over here right now it is not showing any of your model, because we need to generate a volume rendering of that 3D. So we can say that 2D stack image of a DICOM. If I click on this volume rendering setting tool, so over here we can see here our visualizations just by. This is just showing a volume rendering of that particular region. We also have some options for setting the volume background rendering. Let's say if I click on this preset, okay, and we have a range to select any of the preset. Let's say if I select this bone and load the selected preset, close this. So over here we can see this is a tool just for the visualization. And for today's this demonstration, we are going to focus only on this pelvic region part. So to focus on that particular region of interest, we need to do some cropping. Because we are going to focus only on that part. Okay. So to crop our region of interest, we can use some image processing tools. So in the left hand side corner, we can say there we have image processing tab. If I select in the transform tab that in crop tool, okay. So for cropping, we have various options. because you can crop by using this slider in the 2D view, or if you know the values, you can also enter the direct values for the particular focus on your region of interest. Or you can crop by moving this, because we are going to focus only on this pelvic region. So I will not consider the upper part. Okay. We have cropped that region. If I click on this apply, and right click here, press R on the keyboard. If I go to this, okay. So as we can see here that we have cropped that anatomy to our region of interest. So right now we are going to apply a mask. We're going to do the segmentation of that particular region. Okay, so for that we will start by doing some pre-processing. If I start going in this image processing tab and select this threshold tool, let's say that is also available in the segmentation tool, because we have a range of segmentation tools starting from manual to some automated tools. Let's say advanced tool like this multi-level O2 and waterside segmentation. If I click on this threshold tool, here we have a range to select our threshold value, because you can select based on your histogram, or you can select by a profile line. Let's say histograms is you can say have a grayscale value is populated here, so we can identify the lower value and upper value, and then we can click on this apply. Okay. Let's say if I show you how this profile line work for doing the segmentation. If I expand this 2D view, focus on this part and select this profile line and draw a profile line at this region. So over here we can see the grayscale peaks. There are 2 peaks. So this white region is showing as a peak. So over here we can select our lower value and upper value for segmentation. And we have a tool that is Sttp shed for bone, muscle, fat, and skin. So if I select this histogram, and we are going to do manually, like how you can do this by manually. Okay, let's see if I scroll this. Okay. So if I focus on this slice, that's look fine. Okay. So if I scroll this, so right now we can see here in the 2D view, the color is changing to red because we are going to apply a mask. Okay, that value is okay. Okay. So we have selected lower value and upper value, and we have options to fill the cavity in the resulting mask. And if you want to keep the largest resulting island, then you can tick on these 2 tools. You want to apply all slice? Yes. I want output as a new mask. If I click on this apply, if I close this, and if I generate a fast preview, okay, if I expand this 3D view and press R, so right now we can see here that there is a large amount of noise is present here. So to remove these noise, you can use some tools like such as this mask flood fill tool, because we are going to remove these noises present here. Okay, to remove this noise, let's select this mask flood fill tool and select this resource as our active mask, mask 1. An operation, because we want to remove these island type of noises. Okay, then connectivity, let's say if I want as a new marks. Okay, let's say. If I expand this, over here we can see that we have identified the noise is present here, and we don't want to keep this noise, so we can turn off these here. You can see it. And we also have a options. Let's say you can delete that mask, expand this, and you can generate a fast preview. Okay, so now we are going to split all these anatomies. Let's say femur from this left hip, and then sacrum from this right hip, this femur. Let's say for this we need to use, okay, for this we are going to use this split region tool for splitting the two region, more than two region. For that it asks me about the target mask and markers, so we need to create a marker. Okay. So first I'm going to tell you how you can do that in 2D. If I expand my 2D, you can here select your brush size. Let's say if I select my brush size is this, okay. And over here you just need to roughly paint the two surfaces that you want to split from that particular region. Okay. So you don't need to be very accurate. Okay. If I click on this apply, I close this, press R, generate this. Okay, so we can say that we have splitted two regions, because, and we are also going to split that left hip from that sacrum part. Okay, so for that part I'm going to show you how you can do that also in 3D view. Okay, let's say we don't need that old mask, we can delete that marker. We also don't need that. For that is our active mask, and we are going to create a new marker. If I generate this and zoom here, okay, so I will show you how you can do that in 3D view as well. Let's say over here you just paint that surface that you want to split. Okay, and then you can click on this apply. Okay, and for better quality, you can click on this model preview. Because this model preview gives us the actual representation in better quality. Okay, but for this part, let's say we don't need these markers, so we can delete that old mask. Okay, and we can rename all the parts. This red one is our, you can say, left femur. Okay, that is our right. And this green one is our, we can say, left femur. This is our, we can say, left hip. This one is our right hip. This is our, we can say, sacrum. Okay, if I generate a fast preview. And now we have segmented all the region. For better quality, we can do some post-processing. Let's say for go to image processing tab and select, if I isolate this, let's say we are going to focus on this right femur. If I isolate this and press R, so over here we can see there are some cavities which are open. So these, so we need to fill these cavities. So for filling these, we can do that by manually, or we also have some automated tools. So first I will show you manually how you can fill these cavities. Okay, so for that I'm going to select this paint tool. What I'm going to do, I will paint every third slice over here. Which I see any open cavity. I zoom this. So over here we can select the brush size. This I want to paint. So whenever we see any open cavity, we will paint that region. That is also open to the boundary. This is a manual operation I'm doing. And then later I will show you how automatically you can do that also. If you want accurate result, you need to spend you can spend more time on that part if you want better accuracy. Because we are going to paint every third slice. Okay. Okay, so if I expand this over here, we can see. So right now it is showing as a blank. If I generate this fast preview, so I have filled that region. Okay, and if there is still any open cavity, for that we can use some tools like this close tool. Here, if I enter the value as a 3, and if I click on this apply, if I generate this fast preview, okay. So right now there is no open cavities except this. Okay. For better quality, we can use some fill gap tools. Let's say fill gap. Yeah, selecting this. I want to fill. If you want to fill that region also for 3D printing application, let's say I select this and apply. Generate a fast preview. Okay, so we can say we have filled that region. Okay, and let's say if still there is any open cavity, then we can also fill that cavity. And then we can apply some smoothing filter, like we have range. We can apply recursive Gaussian. So we can enter a value of 1.5. That is fine. So this value can be identified based on your experience, because when you are going to work on that particular part, then you will be able to learn how you can identify this smoothing value. Okay, so now it looks fine. Okay, so the same thing can be applied on all the parts. Let's say for left hip, right hip, sacrum, if I generate this fast preview. Okay, so the same thing you can, the same steps you can follow for the rest of the parts. Isolate this, and now we are going to export this right femur as a STL file for 3D printing application. For that, for 3D printing, let's say if you want to see that, for that we need to create a surface model. Let's say if I expand this here, we have options to create a new surface model, FE model, CAD, we can say CFD. Let's say if I select this surface model right here, if I generate this fast view, okay, and if I click on this full model, okay, So to see the quality of meshes, you can see here. So right now it is a surface model to see. You can click on this view and label this, scroll this to see like how this surface model look like. You can see here. Okay. And if you want to provide the internal lattice structure to that part, okay. So we are going to provide an internal lattice structure for giving the strength to this part, because in 3D printing, it will create some problem. Let's say if we are going to provide internal lattice structure to that part. For that, we need to create a 3D preview. Okay. For that, we need to create a surface. Okay. And we have generated a model preview. Okay. Now we are going to generate an internal lattice structure. So first, we need to convert this mask into surface for providing the internal lattice structure. Okay. For that, let's say if I click on this model preview and convert to surface right here. So we have converted this. Click on this model preview away and click to surface tool. Then select this internal structure wizard tool, because we are giving the internal structure, because the internal structure wizard tool allow you to create an architecture within a CAD model in order to reduce its volume. Let's say if I click on this rest, over here you can see the CAD dimension. Click next. If you want to provide the cell thickness, so you can select that. Let's say if I provide a cell thickness of 2 mm. Okay. Next, we have a range to select. Let's say we are going to provide internal structure of that kind of lattice structure, unit cell. We have a variety of selecting the unit cell. You can provide in that, or you can select in that also. Let's say for better use this. Okay, and if I click on this next, so right now it is generating the internal structure of that femur part. Okay, to see the internal structure, we can go to this. Okay, over here we can analyze our internal structure. Because we have provided a cell thickness of 2 mm, that's why it is showing here a gap of 2 mm. If you don't want to keep the cell thickness, so you can enter a 0 value. Okay, and then you can export that part to the 3D printing application. Let's say if I go to this 3D view, then we have options to export. So you can export as a STL file in any of these format, and you can click on this export. Okay, so you can click on that. So STL file was exported. So at that time, if anyone has any query, then you can ask, you can unmute yourself. So I will move on to another project where I will show how I have performed this task on a whole sample. So let me just switch my screen to another project. So this is the final data set that I have prepared. If you want to see the volume mesh, you can also see model or full model. That full model. If you want to see the quality of mesh, let's say for proximal femur left, press R. You want to see the mesh quality, you can over say here, there is no error found, the frequency in the Jacobian form. We have a range of metrics because while doing the research part, this part is more important. Let's say if you want to see how it looked like, that is fine. Okay, so you can see here the coarse mesh, the mesh quality we have selected as a tetrahedral, so that's why it's showing like a tetrahedral mesh quality. We also have options for mixed tetrahedral and hexahedral, and you can configure your model. Okay, so this is the all that I have prepared for today's session. If anyone have any query, you can ask, or we can end this session. I would like to tell something that there are some available research area for ortho engineering. By using the SimpleWare software, you can investigate the biomaterial or biomechanical properties of any bone. We have options for, you can also, there is a new material development for improvement. You can develop a new material for implant. You can or artificial implant for human organs and higher accuracy of CT image based 3D model for finite element analysis. What we have did today for this project, we have imported a CT scan DICOM images, and after that we have separated hard tissue and from the anatomies, and also created a surface model for 3D printing export and for finite element mesh for a simulation purpose, for simulation export. Okay, so if anyone have any query, you can unmute yourself or ask, or otherwise we can end this session now.
Good afternoon, sir.
Yeah, good afternoon, sir.
So the input image in concern with our software. So can we acquire an input image from MRI scanner machine, or only CT image can be given as input, sir?
You can import in any of your formats, sir. Like you can import in, you can import your MRI images or DICOM images or CT scan images.
Okay, okay, sir.
In the presentation which I have showed you earlier, that the formats you can import.
We have. And so for rapid prototyping, what will be the output format of SimpleWare after all the operations have been done?
You can export your project as a STL file for 3D printing application, for 3D printing for rapid prototyping.
Okay.
And we also have an option for nubs for export to CAD packages.
Okay, okay. Thank you, sir. Thank you.
Thank you so much.
Sir,
Yes,
one question from my side. Sir, before giving to the that is before printing 3D before 3D printing, how can we validate whether the validation can be done the software itself, or what you have done is correct or not? You have to validate, no, sir. Or how it could be validated?
So validation of a model has to be done by the user itself. I mean, you will have to manually check that. You can check that in the software, whether the model generated corresponds correctly with your actual anatomy or not. So that can be done. Yes.
There is no, that is a result can be derived with the help of the software, sir.
What kind of result, ma'am? Validation result?
Validation, I'm asking.
Okay. So, okay. I mean, I believe there is a service deviation analysis is also present. And if you have a model to compare it with, because for validation, you need to compare it with something. So if you have to compare it, then you can do it using a surface deviation analysis. Other than that, Simpleware produces watertight and very robust STL files, which have no self-intersection, and quality of the mesh, of the surface mesh, can be checked using some tools that are already available.
Okay, sir. Okay.
And quality of the segmentation also can be checked. But
Okay.
Validation of it with the actual anatomy has to be done by the user itself.
Okay, sir. There is no procedure inside that software.
I mean, can you elaborate on this? I mean, how do you want to do this? I mean,
Then the software itself cannot validate. So, for example, it is ready for the 3D printing, and it is very accurate.
Okay.
So that validation can be done with the software, or you have to go for some other validation.
I believe there are some tools available in the software, like local surface correction and similar tools. I mean, which can help you to achieve even more accurate data. Yes, some tools are available. Maybe not direct tools, but some tools are available which can help you in doing the validation.
Okay. Thank you, sir. Thank you, sir.
Yeah.
Okay, fine, ma'am. That is all that I have prepared for today's online session. So we can end this session now because my presentation is over.
Yes.
So thank you so much, sir. And thank you, PSNA College, for giving us this wonderful opportunity. Thank you so much, sir.
Definitely, participants. It is a great honor for me to deliver a vote of thanks for session 2. On behalf of Department of BME, PSNA CT, I'd like to thank Mr. Jayasu, Senior Application Manager, and Mr. Pradeep, Integrated Microsystems, Gurudhan. PSNA CT and Biomedical Department have a strong relationship with Integrated Microsystems. We have been doing a lot of things like, so before we had a great experience of handling those things with Integrated Microsystems and Synopsys software. So today's session gives us a great hands-on experience in the topic of 3D printing, which is one of the most recent trend which is identified by AACT. And there are a lot of scope for doing research also in 3D printing. Thank you, sir, for your acceptance in today's presentation. So thank you so much. Participants, next session will start by 2 p.m. sharp on the same link. So we'll have a lunch break now, and we shall start the next session by 2 p.m. Thank you all for joining us for the forenoon session. Thank you.
Thank you so much, sir. Thank you.
Thank you, sir. Thank you.